Our next speaker is Mark Brongersma. So he did his PhD in 1998 at Amol. Then he moved to Caltech for a postdoc, a few years, very successful. And then eventually becoming full professor in Stanford. That was in 2001, 2002, in Stanford?
2001.
2001. So Mark is a solid reference in nanophotonics with plenty of things in his career, plenty of accolades as well. So I encourage you to look at his website, and you will find wonderful things.
Thank you. Okay, thank you. I hope the microphone works. Can everyone hear me okay? My volume is going up as I speak. Great. Well, it's so nice to be here in Barcelona. Very nice to see many young people in the field. I think we're in good shape. I'm going to talk a little bit about how light can manipulate it with atomically thin materials that support materials excitations, quantum excitations, as an alternative to using Me resonances or plasmon resonances. And this work has been done with a whole bunch of different collaborators at Stanford and around the globe. Was initially led by Jörg van der Groep in my group, who's now at the University of Amsterdam. And here's the story in pictures. We have this whole wealth of 2D materials going from graphene to hexagonal boron nitride to transition metal dichalcogenides that have metallic, phononic, semiconducting, interesting properties. They can be stacked on top of each other, and they show very strong tunable resonances. So could we use these highly tunable resonances to pattern new types of optics that maybe we can turn on and off and demand, or allow for dynamic steering functions? And ultimately, these quantum materials, when we start using quantum excitations, such as exciton resonances or phonon resonances, problems with dephasing and non-radiative decay will come up, and can we fight them again with photonics? Here's just a brief introduction to warm up the audience. This is how our group thinks about the field of nanophotonics, that all of these technologies where we manipulate light are fundamentally limited in their performance or functionality by our inability to manipulate light at the nanoscale. And there are many examples in going from solar to displays to chemistry, communications, where starting to manipulate things at the nanoscale can help achieve new functions and higher performance. So I've borrowed and expanded this nice slide from Philippe Lalanne and Pierre Chavel, who have shown for development of optical elements in particular, how one has gone from dielectric Fresnel-like objects or diffractive optical elements to binary blazed gratings that are now would be called metasurfaces, to Eris Husman working on geometric phase, and then using all sorts of new design and computational tools to ultimately manipulate fully the light field, control aberrations, go to high quality factor systems where one very selectively can manipulate one frequency of light or one polarization state of light. And one of the next frontiers is to try and think about how thin can we make such optical elements, and how dynamic can we do this. And there are many interesting scientific promises and challenges, and also many technological challenges. One of the, I think, the greatest opportunity in the age of sustainability for us is that we can start using more common materials such as silicon or silica, pattern them, and achieve functions that typically would be used or only achieved with more complex, maybe not sustainable materials, not earth-abundant materials. And now also the recycling processing is becoming much simpler if we can just use one material for one type of optical element. There are new opportunities, and many people are pushing in this direction, when we can make such optical elements dynamic. We can make new types of displays that not only provide tunable color, but can redirect and control the entire light field and polarization states. We can achieve new types of imaging, computational imaging combined with computers, beam shaping and steering for LiDAR, dynamic holography, adaptive optics, cascading dynamic structures to mimic the features of real neural networks, and there are all of the challenges in building these things. We need high diffraction efficiencies, high numerical apertures, but in addition here, we want high speed of operation, low cost of fabrication, and also when we start driving these at high frequency, we would like or love low power operation, as the density of nanoscale elements are similar to the electronic transistors are pushing there on the chip. We get to similar power consumption issues as we see on silicon electronics computers. Here's just a gallery. I'm not going to explain all of these. A gallery of different topics that in our case, our group has worked on, inspired by many of you here, where we try and use materials such as indium tin oxide, stickman gap resonators, where ITO allows you by charge injection unity index changes of materials properties. Same for MEMS, phase change materials, electrochemistry, electrochromics, microfluidics, where we change the dielectric environment of scatterers. All of these different approaches are out there, and they have in common that we need to manipulate light in such a thin layer that we need order unity changes in either real N or imaginary K parts of the refractive index to actually have a notable dynamic impact on the optical wavefront. So how do we do that? Well, I studied in detail all of these beautiful structures. Here's one from Federico Capasso, where metallic nanostructures are used, and their strong light scattering properties due to the excitation of surface plasmon resonances, where we can drive little electronic currents under the influence of light that effectively rescatter light. We've worked on Mi-resonant silicon metasurfaces, where we can excite Mi-resonant modes where light circulates inside the structure. Because of the high index or high conductivity, these structures have very high diffraction efficiency if we put many scatterers together, but they're very hard to tune. Metals and semiconductors, through doping or charge injection or application of fields, show very weak modulation. So wouldn't it be wonderful if there was something that's enormously tunable and shows very strong resonances? And I think one of the nice things is that one can use materials resonances that are distinct from what I think of geometric resonances that we can tune by manipulating the size and shape of structures. Here, we need to find materials, such as atomically thin semiconductors, that can support very strong excitonic resonances. And hopefully, we can use them in the same way as Mi and plasmon resonances, but in an atomically thin form factor, and maybe ones that are highly tunable. Another nice thing is that exciton resonances in these atomically thin materials, and also some quantum well materials, dominate the optical response at room temperature. And furthermore, they can provide some of the highest speed electrical responses. So we could operate excitonic lenses or systems easily at something like 100 gigahertz. So very interesting opportunities. So work before us nicely showed that if you, for example, layer 2D materials and in specific ways carve them, you can manipulate the propagation phase and have some focusing. People have done amplitude control, like CWQ's work, where he patterns a zone plate in a single or multiple layers of 2D materials and allows focusing. But in these works, not the optical resonance of the materials themselves really were noted, and it's very interesting and important, I think, to be able to identify what resonances play a role and see whether we can imprint those resonances onto optical wavefronts and then structure light or manipulate light with them. So, let's see, there we go. So we're interested in, for example, excitonic resonance. Exciton resonances are particularly strong if you have a semiconductor and you shine light, generate an electron-hole pair. They can provide features below, about the Coulomb binding energy below the band gap of a material. And if you go from a three-dimensional to a two-dimensional structure, actually because these atomically thin layers bring the electron and hole in plane. Actually, there will be some fringing fields in a lower, typically lower dielectric medium surrounding it, increasing the binding energy of the electron-hole pair and making these exciton resonances even stronger and more well separated from the band gap. Now, work, for example, from Lin Yu Zhao's group at North Carolina showed that if you look at the band structure, you can have different types of excitons that you can excite here in WS2, tungsten disulfide, atomically thin layer. You put it in a gating configuration, and if you look at the effective N and K by applying voltages, you can see that we can get unity order changes in both N and K as we manipulate it. So highly tunable optical resonances. Furthermore, there's this nice work from the groups at Harvard and ETH that show a tiny little flake of molybdenum diselenide, an atomically thin semiconductor that supports strong exciton resonances, and they put it in a Salisbury screen type configuration with a 2D layer spaced away from a reflective silicon, and they see in the undoped state, they see a strong reflection from the little flake, and when they inject charge via this little lead, it goes completely dark. So unity order tuning of reflectance properties. And when I saw this with my group members, we thought, oh, we need to pattern this and make all sorts of metamaterial optics out of this. Okay, well, here continues the story. It turns out that if you look at the reflectance in this experiment versus wavelength right near the exciton resonance, at 4 Kelvin, where they did this experiment, looks like a super strong reflectance peak. But as you increase the temperature, and this red line, which looks flat almost on a linear scale, that's what they call the strong exciton resonance at room temperature. So can we really use it? And the annoying thing, and this is I guess, suffered by many quantum materials, that non-radiate, as you increase the temperature, non-radiative decay processes, dephasing processes, phonons come in, strain the material and shake this exciton resonance and therefore broaden it. All of these things will limit our ability to use these resonances. So what can we do? Well, here's the challenge. Dephasing and non-radiative decay limit these nice quantum excitations that directly appear in the linear response of these materials, so we can use them, but are there ways to, at room temperature, to make things practical, allow us to use the optical and electronic materials, improve them somehow. So we don't want to cool down, that seems to work. We want to do this at room temperature, maybe improving growth, getting rid of defects, thermal annealing treatments, chemical treatments. Older superacid treatments have been used to enhance photoluminescence. I'll show you that strain can be used to manipulate the band structure, thereby the optical resonances, materials resonance of these materials, and improve their quality. But also by bringing these 2D materials near patterned open plasmonic cavities, it turns out that we can recover some of the coherence that we need to make dynamic optical devices. So let me start by giving you the example of strain. So here we do a simple experiment. We dig holes in a silica wafer, transfer by now known stamping techniques a layer of 2D material or 2D semiconductor, in this case tungsten diselenide, and here you see a top view bright field reflection image of 2 holes on which we stamped these materials. Sometimes you have 1, sometimes here the blue part is 2 atomic layers, and you can see what happens as you apply air pressure. You bend this membrane, like the membrane of a drum, and start to strain it just a few %. And it turns out that these materials are very strong. If you look at various materials you know, and some of the 2D materials, and their Young's modulus, their breaking strength, if you take the ratio of these, you can find out how much you can strain these. So some of these you can strain, like a monolayer of MOS2, you can strain 6-7%, thereby majorly tuning their optical properties and materials resonances to manipulate maybe in the future metasurfaces. So here's an example what happens if you go to room temperature and you measure the photoluminescence, light emission signal, as a function of energy, in this case of a tungsten diselenide material, where you see an exciton resonance has a line width of almost 50 millielectron volt. And now we apply pressure, strain the membrane, you see a notable shift due to the strain, but also, which is more exciting, a narrowing to about 20 millielectron volt, maybe 5 times more than one would get at 4 Kelvin. So a major beneficial effect, and one can understand this. We've done this with the help of Tony Hines, who is a spectroscopist for 2D materials. He has looked at the line width of different contributions of different processes as a function of strain, where it's maybe most easily seen in this Venn diagram, the different processes. If I excite this semiconductor, I could get a radiative decay. That's what I would like. But also there could be intervalley scattering that causes some dephasing, or scattering to a neighboring valley in the KQ point. Well, it turns out that the straining of this material lifts this KQ valley up and effectively switches off this dephasing process. So that scattering process is no longer possible, and the line width narrows. So the phonon contributions due to intervalley scattering that contribute to the line width, as we strain it, reduce according to a theory produced by Tony Hines and people, and we are left with a much smaller line width that's now limited by intravalley scattering and radiative decay. So there are interesting ways to start manipulating phonons and band structure to make optical resonances better. Very different than thinking about how do I engineer my metallic particle or my Me resonator better to get more effective scattering. So then let's make a lens. Here's a first lens that was made by Jorik van der Hoop by just patterning in orange here a layer of tungsten disulfide with a strong exciton resonance. We can illuminate from below, just like a conventional zone plate, the material that's remaining, not etched away, causes scattering, constrictively interferes into a focus. Here you see a finite difference time domain simulation where the red is the substrate, the light comes from below. Each of these patches scatters light to a focus, and we've modeled this just by taking the susceptibility that we can get from a ellipsometry measurement on an infinite film. So this works. The redirection efficiency is very weak, in this case about 0.1% or so. But still, in the focus, if you have a big lens that concentrates light to a diffraction limited spot, you can get notable intensities inside the focus. Here are some of the lenses shown in optical images. You can see, if you look very carefully, some zone plates etched. It's single monolayers that we're etching away, so the contrast is small. Note that it's large scale. With CVD, we can already grow this over 4-inch wafers. If you zoom in, you can see here the reflection image. You can see, I think, the zones here running around, and there's some metallic electrodes here that we use to electrically address and gate this structure. So that goes into an electrochemical cell. You can see in here maybe 12 different of these lenses inside with a little bit different parameters. We can gate these using an ionic liquid gating scheme where this cell inside schematic side view has a substrate. There's an ionic liquid inside. Here's a patch of 2D material lens. Here's a gold reference electrode. This ionic liquid you can, to first order, see as a molten salt with positive and negative ions. And if I apply a bias between here, these two, the gold reference and the tungsten disulfide pattern, if I accumulate positive ions on the pattern and negative ions on the gold reference, here I can pull in, because of the presence of these positive ions, pull in electrons inside my 2D material and effectively gate it, extremely efficiently change its optical properties. So here, without doing a lens, is a reference structure. Here's just a little patch of tungsten disulfide with a trench etched around it. and a little metallic finger that can inject electrons into the patch. And here you see the reflectivity measured from this patch as a function of the illumination wavelength. And you can very nicely see here the exciton A and B resonances of this particular semiconductor. Very strong resonances. Note that this is the reflectivity scale is cut off, so it's just 3 to 4%. But so there's notable reflectivity for a single layer, but ultimately, in absolute terms, it's small. And if you electrically gate it, this resonance turns completely off. Maybe there's a little bit of trion formation here, but for those working on silicon and Mi resonators and plasmonic resonators, seeing a resonance completely turn on and off, it's pretty satisfying. So that's good. The tunability is large. The absolute scattering is maybe weak, but maybe we can work on that. So we can then use this material, pattern our zone plate lens. We put our lens in a confocal microscope. We can raster the collection volume behind the lens, see how light from the location of the lens here comes to a focus. We can capture the light in the focus and see that the focusing efficiency, the amount of energy that we illuminate the lens with, and the energy that ends up in the focus. If we divide these two, that's we define as the focusing efficiency. Note, extremely small dephasing processes and non-radiative decay, but there's an interesting feature in it nonetheless. So why does it have this interesting spectral line shape? Well, it turns out we're measuring truly the susceptibility, the optical response of this material. If you think of this lens with different zones and we illuminate from below, just a little bit of light comes straight through to the focus, but most of the light that ends up in the focus is scattered from the different zones of the ring. So the light that comes to the focus is determined by the scattering properties of these materials, which is linked to the susceptibility. The scattering power of each of these zones is linked directly to the dipole moments you induce in these rings, and therefore the susceptibility squared. So if you look at the susceptibility, the absolute value and the phase for the tungsten disulfide, you see peaks appear near the A and the B exciton resonance of these material. And the absolute value that tells you the scattering efficiency shows exactly this undulation that we see in the focus. We can turn it on and off. We can see at 0 volts the nice exciton-related feature. Near here 615, the exciton resonance. If we inject carriers, that feature disappeared. So it's nice. We can, modulate to the left or the right of the resonance. You can see the modulation, very reproducible. And if you think about it, it's quite nice. We have apparently a way to, in the focus, collect much more light from this two-dimensional material, do spectroscopy on it. We can learn more about exciton resonances with a highly enhanced signal to noise. We can indeed conclude that optical resonances and maybe other quantum properties can be imprinted on optical wavefronts. So can we make new types of optical elements that go beyond building lenses with basic linear responses of metals and semiconductors? Can we learn more about tunable quantum properties? And as a practical matter, can we go to higher diffraction efficiencies? Okay, well, to think about how do we go to higher diffraction efficiencies, it's nice to think about what exactly controls this line shape. So we've done some experiments where we put one of these 2D materials on top of a substrate and do a basic reflection measurement. And ultimately, we want to learn, is the reflection of that very similar to the reflection of a layer of silicon? Or is there something unique about these quantum materials because of the non-radiative decay, dephasing, etc.? So if you analyze this system, there can be a reflection of the 2D material, there can be a reflection from the substrate. The reflection from the substrate here is just linked to the index contrast between the substrate and the superstrate. but then there's also the reflectance amplitude, reflection amplitude of the material of interest that scales with the susceptibility, the linear response of this material that has the exciton response encoded in it. Now, if you measure the reflectance, you get annoying interference between these two that's going to determine the exact line shape. You will get that your reflectance is a sum of the amplitudes squared, and this has contributions of both reflectance of the 2D material, the substrate, and some cross terms. And you can indeed see that if you build a liquid cell where you can have your 2D material on the substrate, and you put different index liquids on top, that you can manipulate the line shape that you see in the reflectance. It's sort of interesting that typically you get from your sample strong reflectances, but now the reflectance of your atomically thin layer is about 1%, but also a glass slide, which you may use as a substrate, is on the order of a few percent. So actually, they're similar amplitudes, so you expect strong interference effects in the reflection measurement. So you can see line shapes as you change here the index of the liquid that you put on top of the 2D material. You can see here at 650 nanometers, you can either see a peak or a strong dip. So it's important to know as you start analyzing these line shapes and look for possible quantum effects to know just the basic optics here. And you can, for example, choose the index to match the index of the substrate, and then you can carefully look at the reflection properties of the material itself. So that's shown here. You can put a liquid on top that has the same index as the substrate, so you can get rid of this substrate reflection and carefully look at the line shape of the A and B exciton resonances. And we have applied a 1D transfer matrix model that came from Misha, proposed by Misha Lukin and team. It basically takes into effect that you can excite this material, typically the reflection of a substrate, and the material you put on top will be coherent, but now you can excite your exciton population. The exciton population can cause a polarization that slowly can decohere with respect to the glass substrate, and that's something you have to take into account. And it turns out here at room temperature, well, the quantum and classical model are somewhat similar. Maybe the quantum model fits a little bit better than the classical model. If you believe the quantum model, then you can extract radiative decay rates that nicely match the ones found at 4 Kelvin, non-radiative decay rates, and also the dephasing rates. We're exploring a whole bunch of different semiconductors at the moment to see whether we can really make these quantum models better. So here's the problem that happens as we increase temperature. So at 4 Kelvin, where we saw this wonderful modulation by the Harvard and ETH groups, where you shine light, you excite electron-hole pairs. The electron-hole pairs can cause a polarization of the material, and they can radiate back light before the electron-hole pairs radiatively decay or start to dephase to produce essentially luminescence. But at room temperature, it turns out that with the 2 MeV radiative decay and the very large amount of broadening due to non-radiative decay and dephasing, basically light comes in, it excites electron-hole pairs, but they either non-radiatively decay or dephase. The resonance starts shaking, and therefore the emission ends up at a different wavelength. It's no longer coherent with the illuminated beam, or it decoheres with respect to the reflection of the substrate. So what if we could use photonics? We're all about photonics here. So here is the concept of what we wanted to do. We're going to put our 2D material at room temperature above a metallic structure in which we pattern a grating. And if this grating wasn't here, well, light would excite the 2D material. It wouldn't produce much reflection because of non-radiative decay and dephasing. But now there's an opportunity, if I generate a grating, to excite coupled to a plasmon resonance. I can get high fields in the excitation, so I get the fields of the optical beam by coupling to plasmon resonance on the surface, the excitation fields for this tungsten disulfide higher. And also, the hope is that the excitation in the tungsten disulfide can decay to the plasmon before non-radiative decay and dephasing processes happen. And if the plasmon metal is low enough loss, it can re-radiate it back up. So we pull out the energy from the exciton. We interact with it, we pull it out before unwanted processes take place, and things could become coherent again. Okay, so here's the schematic picture of this. Light comes in, I make a grating in this metal surface, I couple to plasmons, plasmons excite excitons, excitons excite plasmons, plasmons decouple. And here's the structure that we made. In K space, I take this surface plasmon of a smooth metal by making a periodic grating. I fold that back, and I want to align my plasmon resonance dispersion exactly with the exciton resonance. Then I get the strongest interaction in practice. So my student Sitong Lee made many of these samples with gold pads to connect to the 2D material, and metal pads of silver that are all patterned with different periods. And by using different periods, he could nicely move the reflectance dips related to the coupling to surface plasmons and move those around in the area where we have an exciton resonance. Now, we do this, we stamp our 2D material on top of our silver pad. There's a reference pad without the 2D material. There, the reference pad, we can nicely measure the dip due to the excitation and of the guided surface plasmons. It's nicely aligned with the exciton resonance of the 2D material on the reference pad. These are aligned, so we should strongly see a coupling. And here's what our coupled mode theory suggests, that if we make the right period grading, here's one unit cell, we can notably enhance excitation fields, and we get a reflection modulation in theory that's about 20%. So an atomically thin layer with the help of photonics could maybe bring 20% modulation. So I think my time is up, so I can tell you more about the coupled mode theory for this. If you're interested, let me just finish by showing the results here in experiment. We don't get fully 20%, but here's the reflectance measured as a function of wavelength near the exciton resonance and extracted, although it looks like small changes by charge injection. Here the reflectance ratio goes up to 3, and maybe there's almost a 10% difference between the on and the off state. And by leveraging this, we can also make things that now can steer or redirect beams dynamically. Here's one grading with a chirped array, has a 2D material stamped on top of it, and it's very nice. You can see here the diffraction efficiency of this grading at different wavelengths, and as you tune the wavelengths, you can see that at the exciton resonance, suddenly you can have the exciton redirect the light to the first diffracted order, and then if you move off the exciton resonance, it's just a regular grading again that mainly reflects the light, normal instance. So you can see up to 40% going due to the presence here of the exciton resonance. 40% of the light gets redirected. If you go off the exciton resonance, this disappears again. So, in I guess short, I want to really bring your excitement to exploring not only plasmonic me resonances, but there's a whole zoo of different resonances that we can start exploiting in atomically thin materials to make atomically thin, highly tunable optics. And there are many interesting, I think, photonics approaches to make these materials viable at room temperature. So thank you for your attention.
Thank you very much. Well, this is open for questions from Javier.
Thank you, Mark. Very nice. In this last part, when you couple the excitons to your plasmonic structures, you seem to play with the decay rates and so on, but you don't seem to see splitting, polaritonic, hybridization. Why is that? Because you are having the plasmonic field sufficiently separated for the exciton, but not too much, so that you decouple. So,
Yeah.
I mean, people are crazy about going to strong coupling and producing polaritons, but you are not into that, right?
Well, we're also into that. We actually try to bring our 2D materials closer, and then we see, at least in simulation, and now also in experiment, we see things like strong coupling, but it turns out that at the moment we can't make our gate oxides, aluminum oxide, between the 2D material and silver good enough then to also do electrical gating. So at the moment, there's a technological trade-off. We're trying to find better gate oxides to make polytonic feature. We see it. We see it in if in our coupled mode theory, and we believe now also in experiment, but we can't gate it at the moment. But it's a very nice suggestion. That's where we're hoping to go. Yeah, and then a whole range of other things may open up.
With your zone plate lens, you achieve diffraction limited focus. But many years ago, decades ago, Geraldo de Francia anticipated, and now Nikolai Zoludev has brought to life in great detail, maybe he'll speak about it, that by suitably tuning the radii of the rings, you can do much better than diffraction limited. Now, so this is super oscillation. So my question is, can you achieve this better than diffraction limited using your thin films?
Well, that's a very interesting question. I had not thought about it, but there is for sure which I think goes into that theory, there's an ability to make these strips notably smaller, so the exciton radii themselves are on the order of a nanometer. But excitons at room temperature tend to diffuse, depending on what materials you have, maybe sort of order 10 nanometer. So I would say would still give us an ability to place materials with different optical properties and resonances and variations in epsilon and maybe mu in the future at extremely or a deep sub-wavelength scale. Whereas with metals, you have the problem that as you go smaller and smaller in the optical regime, typically these resonances fizzle out. I think these resonances will stay strong and maybe could give an opportunity for what you're suggesting. Yeah, it's a very interesting suggestion. Thank you.
Okay, maybe one last question from John.
Yes, it's a very interesting thought you have there to compete with the phonon decay by enhancing the radiative decay. You do it by introducing these structures, but could it be done by introducing defects into the molybdenum or tungsten sulfide layer and bursting the exciton like a bubble on a defect, say?
Yes, yeah. So I think that's a wonderful suggestion. So people have tried to use bubbles or tiny little topographic features to generate quantum defects that have line width that are notably narrower than the exciton line width of the excitons that are delocalized. So I think that would be a great direction. So if we had a bubble array or a bumpy array, we may also be able to make new lens or higher performance lenses because we can maybe agglomerate oscillator strength at certain frequency. So yeah, I'm very at the larger point. I think there's really an opportunity here, like in the semiconductor industry, how we started controlling defects and strain, and to start manipulating these resonances and get better and achieve effects that would never be possible in silicon, germanium, or metals. Yeah. So thank you for it's a very nice thought.
Very good. So thank you very much again.
Thank you.